I think.
Hello, everyone. I'm glad to welcome all of you to the keynote speech of today. It will be on program repair, patch quality, and human factors by Professor Wesley Weimer.
Excellent. And just before I get started, can you both hear me and see my slides?
Yes, I can see your slides and hear you.
Excellent. All right. So as mentioned, I'm going to be talking about program repair, patch quality, and human factors. And I'm excited to be presenting at the Automated Program Repair Workshop. But can I advance the slides? All right. So I'm hoping to be talking for about 35 minutes and then leave about 10 minutes for questions. And patch quality, human factors, and adoption, I see as some of the bigger challenges facing automated program repair today. We've come a long way in about a dozen years, but I think there's still significant room for improvement if we want to see widespread adoption or deployment of automated program repair. And so I'm going to talk a bit about what I see as the problem, mention some existing deployments and use cases, possibly including one you might not be as familiar with, and then argue that I think issues related to psychology and trust, how humans assess where a patch came from, and biases human developers and decision makers might have are actually just as important as correctness in the deployment of automated program repair. And I'll end with a bit of a call to arms about how I think we might bring in insights from other fields and an increased use of human studies and user evaluations to try to deal with this. If for some reason you have to disappear early, the whole argument of the keynote in one slide, the chain of reasoning, I claim that we as a community care about the broader impacts, the eventual deployments of automated program repair. But a key factor in deployment decisions, even for automation, is human trust. Humans are still ultimately responsible for either deciding to use an automated system or accepting the patches produced by APR. And perhaps surprisingly, research suggests that notions like readability and apparent authorship are actually on equal footing with correctness when trusting patches. And this is true even if the patches are equivalent to what humans produce, or even if they're actually written by humans. And as a result, while I think a number of great things have come out of our community focus on patch quality and overfitting, if we continue to write papers using metrics based almost solely on correctness, those may not capture the full picture for human deployment decisions. And thus, we need end-to-end assessments with humans. So, to set the stage for some of this, especially the correctness parts, I'm going to tell a few stories about early GenProg because it's easy to pick on one's own work. And for example, about a dozen years ago in our first paper on GenProg, we suggested that a number of cool ideas were clearly relevant to the success of automated program repair. We were using a genetic algorithm with crossover to share partial solutions. We had this search strategy. We thought it was pretty cool that we could operate on very small test suites because that meant the developer didn't have to write a lot of test cases. And we thought that using Andreas Zeller's delta debugging algorithm to minimize patches at the end would safeguard quality. And pretty much every one of those ideas was either overturned or supplanted by something better or stronger later. Right? And the primary focus of this story, as I'm going to tell, is on correctness beyond those available test suites. What if you produce a plausible patch that looks good now, but doesn't behave well in future scenarios? And that's often called overfitting in the literature. And there are other potential barriers, such as whether patches were acceptable or maintainable, that we have tried to tackle over time, we as a community. And I'm going to return to those issues later, but for now I'm going to focus on overfitting. And throughout this keynote, I'm going to have in sort of a smaller font a number of references to previous papers, ideally by others, so that you can follow along if interested. And I believe the slides are available on Clouder. So everything about automated program repair seemed cool 10 years ago, but what are the parts that didn't actually work out? And one of my favorite stories about this is that before it was even published, GenProg, a particular approach to automated program repair, ran on two problems: Euclid's GCD algorithm and this very small web server that had an official security vulnerability. And we made up 5 tests for this web server: get index.html, get an image, 404 not found, that sort of thing. And there was a publicly available proof of vulnerability. If you posted something to this web server and specified a negative content length, you could take over the world with a remote buffer exploit. And GenProg's first fix was to just remove post functionality, to delete that part of the program. There are potentially some advantages for that, but we might say, oh, that overfits to the available test cases. Adding a 6th test case that required that post functionality be retained resulted in a higher quality repair. But even then, the patch produced by GenProg wasn't the same as the historical human fix, which was to refactor this legacy C code to use a safe string class in multiple places. Shortly after that, MIT Lincoln Labs was asked to evaluate automated program repair in general and GenProg in particular. And researchers there made a version of a sorting function with a seeded defect. And their final test suite basically checked that the output of sort is in sorted order. Like if you output A, B, C, A has to be greater than B, B is greater than C. And GenProg's first fix, when presented with just that test suite, was always output the empty sequence, because it is trivially something that is in ascending order. Every element in the empty sequence is greater than every previous one. Once again, more tests yielded a higher quality repair. But I mention these sort of examples because I think they're kind of indicative of what we're often thinking about when we say overfitting or patch quality. When we think about why someone might not want to deploy automated program repair, there are a bunch of sort of horror stories like these about patches that are produced that seem plausible, but might not actually be what we want longer term. Sometimes this overfitting can get particularly creative. There was an example in GenProg where a test case basically compared what you produced, what a program produced, to an Oracle text file in the same directory. And GenProg's first repair was to basically change the beginning of main to unlink Oracle text and then call, exit 0. And the particular comparator used would then end up comparing the empty output to the empty file and say, oh, you passed. This is probably, almost certainly, not the patch the developers would have wanted. There is a sort of a side interest in this digital creativity, but it's a bit of a double-edged sword. But it also follows this pattern we've seen of removing functionality or removing output. And since many of these low-quality repairs, especially early on, were deletions, it made sense as a community to focus on better repair operators. Perhaps, the line of reasoning goes, if we could just avoid deletions, that would force the creation of better repairs, or at least reduce the incidence of overfitting. And there is something to that, but it's a complex issue. One of the first critical investigations published about half a dozen years ago looked into just this, and I've called out research question 4, are the reported GenProg RS repair and AE patches equivalent to a single modification that just deletes? And the answer was yes. Well, that line of reasoning could support APR approaches that use different operators. Maybe if you only insert, you can avoid this low quality overfitting approach. And there were some program repair approaches that favored that sort of maneuver. Maybe if we only add conditionals to if guards, if we're only inserting code, then we can avoid this deletion consideration. And I actually think this is a great idea, but it is difficult to make these sorts of things work pragmatically. For example, one of the tools that was first designed to only do insertions or only insert if guards ended up inserting, and false into a number of if guards, which has the effect of deleting the subsequent statements. And a subsequent investigation into this found that as many as 45% of the things that were thought to be insertions were actually functional deletions. And so I definitely think this approach to improving patch quality and reducing overfitting by looking at better repair operators is worth pursuing. But I think it's A, difficult, and B, not the entire story. All right. While repair quality has definitely improved, thanks in large part to many of you, since as we know, GenFrog might not produce the best repairs. In my opinion, from search to templates to semantic constraints to supervised learning, there have been a bunch of great ideas about how to deal with this, but no algorithmic approach or insight to date totally solves the overfitting issue. We have a bunch of good pieces of the puzzle, but we don't know how to solve it entirely. And even recently, we struggle to maximize efficiency at the same time that we're maximizing correctness. Right? And so an interesting recent result, some of these template-based repair systems, which are known to be the most effective in fixing large number of bugs, may be the least efficient. So there are still algorithmic or pragmatic trade-offs. But then how do we explain apparent recent success? In 2017, we saw, in my opinion, the first sort of paper publicizing the industrial deployment or the government deployment of automated program repair. I really love this work, fixing bugs in your sleep, not just the title, but the content. Over 6 months, they've identified and fixed 22 bugs automatically with these sort of genetic improvement automated program repair approaches. The year after that, we heard quite a bit about Repairinator, an automated repair bot. Could you just look through GitHub, say, and find open issues, run automated program repair, and then submit pull requests suggesting candidate patches? Maybe humans would accept them. And although Repairinator was run on a large number of projects and test failures, actually getting patches for bugs to be accepted by humans ends up being a difficult issue, both pragmatically and also because of human factors that I'll return to in a bit. But then, Facebook and its Sapiens static analysis tool had a follow-on project, SapeFix, automated end-to-end repair at scale. And we saw this in a previous ICSI. It was mentioned by Mark Harmon and others when he was giving certain award speeches. And I think this has, I don't know if revitalized is right, but really increased interest in automated program repair because this is being deployed for production systems, millions of lines of code, millions of users. It's really, really exciting. And sure, SapeFix had to focus on smaller classes of defects in order to make this work pragmatically and fit in with a human system. But still, it's something like automated program repair and it's deployed. And that's really exciting. So how do we reconcile these, and why don't we see more? Both, if overfitting were clearly an unsolvable issue, we would expect sort of 0 deployments. But also at the same time, we might expect more. Why isn't there another one of these for 2020 or 2021? Why aren't we seeing the same thing, publicized from Google or Microsoft? And I want to mention a quote here from a few years ago from Andreas Zeller talking about what is automated program repair. Generated repair is the ultimate diagnosis in automated debugging. It tells the programmer where to fix the bug, what to fix, how to fix it as to minimize the risk of new errors. A good repair depends on a good specification. Maybe the advent of good repair tools will entice programmers. Programmers. And I want to just draw attention to, even within the first sentence, automated program repair tells the programmer. And we want it to be as automated as possible. But in many cases, in all cases, even at a high level, humans are still in the loop deciding to deploy it. Right? And so many of you are likely familiar with the previous use cases at Facebook or the fixing bugs in your sleep example. But I want to mention one that you might not have seen in as much detail. The US Air Force put out a broad agency announcement a few years ago. That's a kind of their version of a call for proposals. On the foundations of trusted computational information systems. And somewhere in the middle, they talk about trusted and assured software. And this technical area aims to achieve several independent but mutually beneficial research goals to lay a foundation of assurance across all layers of software development, to maintain trust even as the system adapts during its deployment. And in that view, from the perspective of this government agency, automated program repair is one example of an adaptation that could take place during deployment. Once your software has been written and it's deployed, we deploy this patch. But during that process, trust has to be maintained. Maybe we were okay for liability reasons with deploying this system at the beginning, but now some system is going to be automatically changing it, making a patch. Why should we still trust it? And in the particular case of the Air Force, the focus was on autonomous vehicles or quadcopters. And our university and a number of others, like Arizona or Carnegie Mellon, were involved in this project and ended up deploying automated program repair in flying vehicles that would take off, visit various waypoints and complete missions, but be subject to security vulnerabilities or exploits along the way. And the goal was to automatically detect those security vulnerabilities in flight, hover safely or land, call automated program repair, make a patch, and then complete the mission and return to the base. And I'm showing kind of a public-facing demo version of this because I want to highlight from the perspective of the end user, this government agency, the relative importance of various aspects of this setting. In the upper left, you can see kind of a ground camera. There's an autonomous vehicle. It's flying around in a netted area. There's a security piece of information. Is the attacker able to succeed or not? This particular one was an information leak attack where this quadcopter was taking pictures and adversaries could get access to the pictures. In the lower left, there's your sort of flight simulator, are we tilted, what's happening? And then only in the bottom center do we see actual program repair, the Darjeeling algorithm producing. If your eyes are really amazing, you can probably see the patch in the center and these fitness functions that people are considering. But that's minor from the perspective of the end user. And higher level notions like, did you still fly and visit all of the waypoints, take the pictures and make it back safely to base mattered. And automated program repair was just one way to make that happen. All right. Ultimately, this sort of work was evaluated by a red team, sometimes called penetration testing. That's when you bring in a group of other people not associated to make, for example, a number of defects you're not aware of, sort of like held out test cases in the overfitting sense. And I'm mentioning this here just to give a feeling for, again, this kind of end-to-end evaluation that's being considered for larger deployments. If attackers make a number of security exploits, can you detect them, maybe with automated hardening or anomaly intrusion detection? And then of the ones that you can even detect, can you repair them? And maybe we're able to repair about half of them. But it's really this end-to-end red team evaluation that people are considering. And I mention that example and the Facebook one and others to put the focus on trust. Deployment decisions are still ultimately made by humans. Even if the system itself is entirely automated, there's still a human at the beginning who says, I choose to use that entirely automated system going forward. Overfitting is definitely a key part of that decision, quality. But I'm going to claim it's only one aspect of that decision. And now I'm going to highlight work by psychologists, perhaps less familiar to people in this domain, collaborating with computer scientists to try to talk about this. And one of the things that I'm just going to state for now, but we can return to later, is that deploying automation depends on trust. And you can see I have citations for some of those from the psychology literature, Journal of Human Factors, or even from software engineering. You can take a look at when things like SLAM were a tool that was deployed at Microsoft Research. There are a number of models for this, like do you have a champion in the group? But ultimately, deploying automation is a cost-benefit analysis that depends on trust. And how could this apply to automated program repair? Well, people have done studies, and one of my favorites involves focus groups and interviews, not with undergraduate students, but with people in industrial deployments who had a mean experience of at least 15 years, asking them, under what circumstances would you accept this code into your code base? When would you deploy this external library? Would you take this patch? And they found trust to depend on three key areas. The reputation of the code you're considering, its source, maybe if it's on GitHub, it's reviews or stars. Its transparency, how easy is it to read? Can you see what it's doing? Its organization, code style, comments, architecture. And then finally, performance in the sense of, does it actually do what you want? Does it perform? And that includes things like efficiency, resiliency to future threats, but also functionality and flexibility. And I think a key thing I really want to drive home here is that correctness is just functionality, one aspect of performance, which itself is one of three things that people are paying attention to. Right? So this is important because it emphasizes that notions like how the patch is presented and where it appears to come from are on equal footing with correctness in the minds of humans. And so let me back that up with some additional work. Right? Psychologists have put out a number of models for how humans make decisions, and one of them, not the only, the heuristic systematic processing model divides human cognition up into heuristic processing, where we use gut reactions and rules and social norms to form judgments and make quick decisions, and then also systematic processing, where you have to think carefully, and effortful critical cognition helps us reach a decision. It's not exactly the same thing, but some of you may have heard of this thinking fast, thinking slow sort of model. Same idea. Some interesting non-intuitive results come out of applying this to automated program repair. Reducing the readability or credibility of a patch by, for example, removing all of its comments, actually led to quicker decisions by humans to abandon code, to not trust or to deploy it, showing this use of heuristic processing. But perhaps counterintuitively, degrading code organization, like a spaghetti code, worse architecture, led to more time spent by humans to figure out what was going on in that badly organized patch, and thus counterintuitively, more trust, because more time evaluating it, the humans there were then able to kind of forced to read through it, and they found that it was actually correct and functional. But for me, one of the biggest parts of this is that the apparent author really matters. In a study of about 50 people, both students and experts, they were shown explicit automated program repair patches, but were told deceptively that the author was either GenProg or Bill. And in each case, Bill was given kind of a one paragraph, resume description, is a senior developer, and there was a one paragraph description of how GenProg works. And we're then asked, how trustworthy do you find this repair on a sort of a 1 to 7 scale? And the graph in the lower right is reproduced from this paper. I was not involved in this work. But there was one version where the people participating were shown just the test case outputs, like a GitHub, Travis CI sort of report. This patch causes you to pass all the tests. And another where they were shown both the tests, but also could see the code. And I'm highlighting that kind of in red in this chart. And an interesting bit is that initially, just seeing the tests, people were much more positive on the patch when it was perceived to be written by a human. But afterwards, once they actually saw the code, if they weren't happy with it, their trust went down much more dramatically if they initially thought it was written by a human than if they thought it was written by a machine. And in my opinion, this is important, both because it shows students and expert differences, which I'm not showing on the slide for reasons of time, but also because it's one of the first works to really highlight the importance of provenance, this fancy word for where did the patch come from, and how a kind of a deceptive experimental setup, changing where the patch appears to come from, could really show this kind of bias, these differences in whether you deploy it. So let's dig down into this. In another study, 50 participants were shown high-quality GenProg patches with no overfitting. Now, I know the jokes write themselves. Can you get high-quality GenProg patches with no overfitting? Let's say you generate many of them and only take the ones that match or nearly match the actual human-created patch, or where human experts went in and said, this is actually viable, it's not overfitting. So somehow, by hook or by crook, we find high-quality GenProg patches. And once again, the author was labeled as either GenProg or Bill. And in the graph in the lower right, you can see the perceived trustworthiness on this sort of 7-point scale between whether the patch was labeled as written by a human or labeled as written by a machine. But remember, they're all actually of the same quality. In these experiments, all of the patches actually come from automated program repair. The only thing that changes is the apparent label. And also in this setup, there is no actual overfitting. So there's no overfitting. There's no decrease in patch quality, but there's still a significant decrease in trust, and trust leads to deployment. Apparent provenance significantly impacts trust in APR code. In addition, those experimenters asked participants, what do you think about these patches? And there were 50% more negative transparency remarks about patches apparently written by GenProg, and twice as many positive transparency remarks about apparently human written patches. Remember, transparency is like readability and comments in this terminology. There were also twice as many negative remarks about GenProg's performance. Remember, correctness is under performance compared to human repairs. You may not care about GenProg, but it's sort of orthogonal to this. But remember, all of the patches are actually the same, and all of the patches are actually correct and not overfitting in this setup. And yet, humans thought the ones just labeled as written by a machine were twice as likely to be wrong. All right, so why is that? Well, in a recent study, a number of participants were subjected to eye tracking and medical imaging. Participants were shown historical GitHub pull requests, were told they were written by a man, a woman, or an algorithm, and were then asked to perform standard code review. Would you accept it or not? In this case, all of the patches were actually real and written by humans, only the labels change. And now we've even removed automated program repair from the picture entirely. And in this setup, apparent provenance still impacts trust. For example, machine-written pull requests had the lowest acceptance rate, 78%, compared to men or women that had 80 to 85% in a statistically significant manner, p less than 0.05. And again, this is relevant if we are interested in getting our cool APR ideas eventually deployed. Even when APR is out of the picture, if people think it is, they're less likely to accept those patches. Okay. Critically, though, participants are unaware of this bias. Right? In a similar approach to that previous paper, in addition to statistically significantly lower acceptance rates, patches labeled as machine written received more negative qualitative comments by a factor of about 3 to 1. I think the code generated by machine was more confusing and harder to read, says a human. Machine-generated changes are less readable and a little worse in quality, capable in fewer scopes. Remember, all the patches are actually the same, and they're all actually human-written. The author really influences the perception. The apparent author really influences the perception of a patch. So what can we do? Well, I don't want this to be all doom and gloom, so I'm going to suggest 3 areas that I think are very profitable for us taking ideas into APR. And one of those is machine learning. With the rise of deep learning and neural networks, a lot of machine learning people have faced this same sort of issue of, you can make an amazing model, but you can't explain it to me. Do I trust it? And I want to draw your attention to just one of many algorithms for explaining machine learning, local interpretable model agnostic explanations, or LIME. And not everyone in APR might read KDD. So if you don't, I just want to highlight that within the last 5 years, this paper has received over 5,000 citations. This is a really popular approach in machine learning, where regardless of how you've made your particular classifier, it can help explain that to the outside world. And I think this is relevant for us in automated program repair for 2 reasons. One is that if your APR technique, makes 2 patches and there's the original and maybe this patch you think is better, so you show it to humans, that's implicitly a classification technique. This patch is the best patch, this one isn't good, the original isn't good. So we could use this same sort of explanation. This also includes LIME, a mutation component, which should be familiar to many of us. I know some people in APR are considering already using these sorts of algorithms, but I think they should be more widely used. I also encourage us to draw strength from our friends in natural language processing, things like document summaries and synthesis. From about 10 years ago, or from recently and longer ago, we know that transparency effects like readability and comments really matter to patch trust. We also know from about 10 years ago that adding documentation, even if it's machine synthesized, to automated program repair improves its perceived maintainability by humans. But since then, there are now significantly better natural language processing and code summarization approaches, some of which are in software engineering like venues. And I encourage us as a field to consider more of those, to think of producing not just the patch, but an entire package of associated documentation. Finally, I encourage us to take a view from security or government agencies. we might look more into red team or just external human evaluations. The original Clearview paper, which I really love, featured a great red team evaluation against their approach running on a web system. The quadcopter Air Force work I showed you earlier includes one. Now, just naively throwing automated program repair patches at a system, you have to take care with that. Some of you might be familiar with the now retracted manuscript in the security community, where people submitted bad patches to the Linux kernel to see if they would get accepted. And that was not ethical, but the RepairNator work and the bias paper I quoted earlier show good examples of how to do that, and even how to do things like work with your IRB to have a deceptive study like that and do a good debriefing afterwards. I think we need more of those external evaluations. Even if they're not red teams, as of December 2020, only 25 of the 253 papers in the Montpellier, I think he's in the audience, thank you, Martin, APR bibliography report a non-author evaluation of patches or tools. So every once in a while, an author will say, I looked at it myself and we thought these were high quality, but only 10% had someone who was not an author take a look. We already know that there's a lot of bias in this world. However, a previous study of about 3,000 software engineering papers found that including a human study can correlate with things like citation counts and your odds of getting a distinguished paper award. And as a result, although it seems effort intensive, I think the more we care about deployment and broader impact, the more we as a field cannot afford to have only 10% of our papers look at external humans for their evaluations. And so in conclusion, copy of the slide from before, we care about the broader impacts and deployments of automated program repair. And a key factor in deployment of automation is trust. Research from psychologists and others collaborating with software engineers and programming languages people shows that readability and authorship are on equal footing in the minds of humans with correctness when trusting patches, even if the patch is human equivalent or human written. So we should definitely be focusing on avoiding overfitting, but even if we perfected that and made human equivalent patches, this would still be an issue. And thus, metrics based solely on correctness do not capture the full picture of the use of automated program repair. And if we want more of these deployments like SafeFix, we're going to need more end-to-end assessments with humans to help our research address this gap in trust. Thank you all.
Okay, thank you for the great talk. I will open the floor for questions. I will start with my questions. Actually, I think I find several things that is quite interesting being covered in the talks. Particularly, you mentioned mostly about readability and authorships. In authorships, like recently there is actually an incident on the hypocrites commits, and I think that's also really related to like whether it is humans or like kind of fake kind of commits. That will actually I think bring some kind of danger to the community of automated program repair, especially given the fact that it will make like an automatically generated patch being less trustworthy, because that will be kind of be aware that we may introduce some vulnerabilities. What is your take on that?
You know, that's a good question, and I should have been clearer on that slide. When I had that crossed out manuscript and was suggesting that we should be careful about this sort of unethical research, that was, I believe, this same hypocritical commits, I don't want to say paper because it was withdrawn, but effort that you're talking about. And that did make a big splash in the scientific community, especially in computer science or software engineering. With from my perspective, even in the early days of automated program repair, these sorts of concerns were common. I remember within the first, say, year of GenProg, people were worried, even for security considerations, if I know your system is using automated program repair, can I use that, for example, to leverage a weak exploit into a stronger one? Like if I'm an attacker and I know that patches are being fixed automatically, can I exploit the patch or draw attention to it in a certain manner that I know will cause automated program repair to overfit to it to deploy a bad patch that now actually opens up, you know, some greater issue. And so even within the first few years, people were really concerned about the security and ethics of deployment. But that said, I mean, it only just happened a few weeks ago. I don't know what the eventual fallout is going to be. But I do think it's possible to do that sort of research ethically. Martin Moperu or others might chime in. One of the papers I cited hinted at this, but there's a way, at least in the US, and I believe also for European ethics boards, to indicate that a human study you're doing involves deception. And then you have a debriefing afterwards where you tell people what was happening. I think that's potentially as simple as arranging for the study to bring in people and say, would you accept this patch or not, rather than actually having it happen on the Linux kernel live. But neither of those get to your kind of other point about, is this going to be a big reputation concern for automated program repair? It might be. When we see these sorts of 10% biases for, even if all the patches were written by a human, if you say it was written by APR, people like it less. I definitely think that's part of the issue. And to me, in as much as this is a call to arms, this is what I'm asking us as a field to try to get together and tease apart. When people are biased against APR techniques, is it because they're worried about scenarios like this? Or is it because they just haven't seen enough of them deployed? Or is it because you don't get to look into the eyes of a computer? What is it? So I think your point is a really good one. I don't have the answer yet beyond pointing out that bias definitely exists and it is possible to investigate it ethically. And I think the charge for us as a community is to figure out how can we reduce that provenance bias just to help with more of these deployments. Hopefully that answers the question, or at least dodges it well.
Yes, I think you answered it quite well. We have a questions here. Martin wants to actually take over the mic. So,
Martin, I would love to hear from you. Clouder.
I think he is muted.
Microphone check.
Now we can hear you.
Seems to be okay.
I think he is muted.
No, I'm not. Microphone check.
Now we can hear you.
Okay, so just for you to know, so there is a latency of about 20 seconds from you here, KDH to Cloud Air. So the conversation is hard. So I assume that you can hear me. I would like to, and there is no echo anymore in theory. Very good. Thank you, Wes, for. So there is no latency in the chat, so that's easier to work with. So thank you very much, Wes, for the keynote. Much appreciated. And let's go deep into ethics and really about the business. Okay. Let's say the administrative question of ethics, because ethics is a philosophical question and also like an administrative one with IRB and so on. So you mentioned your FSC paper where you showed pull requests to people. Can you tell us more about what you did for this experiment with respect to asking for permission to some boards, and then what you did with respect to the humans who were involved, what you told them before and what you told them after the experiment?
Definitely. Thank you, Martin. So for that paper led by my student Huang Yu, we first worked with our local IRB or institutional review board, but in other countries that's sometimes called an ethics board, which is a part of an organization, be it a university or a company, designed to do ethical human studies. And we had to write out our protocol in advance and say we would bring people in, show them this, and they had to improve it. And from the perspective of psychology, an experiment where you are lying to your participants about what's happening is called a deceptive study. Probably one of the most famous ones of those is the Milgram obedience experiment, where people thought they were shocking someone to death who was giving wrong answers to a memory test. And after that study, humanity kind of got together and said, we want to be more careful about that and regulate that. So the way our study worked is we brought people in And because we were doing this under medical imaging, they were, kind of very clearly not talking to GitHub. They were in a separate room, and we would show them patches and say, here's the person who wrote it. Here's the, git commit comment. Would you accept it or not? Here's the diff, and they would indicate yes or no. And then afterwards, the big difference, especially in the modern world for these deceptive studies, is that you have to have what's known as a debriefing session, where before the participants leave, you sit down and say, here's what we were really going after. We said this was written by a man, a woman, or a machine, but in fact, they were all actually written by these human developers. And you can't say this at the beginning because you're trying to get an unconscious bias. It would influence the results, but you make sure you tell it at the end. So I think the two key differences between what we're proposing, what we've done, and what we might have seen in the news are, A, the output of what the participant was doing never actually influenced the real world. They were not actually accepting patches on GitHub. We were just marking down in a spreadsheet if they said yes or no. And then two, they signed an informed consent form at the beginning and had a debriefing at the end to indicate, I'm okay with participating in this, and now before I'm leaving, I know what had happened. And I'm not saying that this is a perfect system, but I do think that's a way to carry out this research. Now, there is an issue of ecological validity because they're not actually people on GitHub. Maybe they're holding things to a different standard when they're in the lab than when they're actually at their job. That's an additional challenge for us. But since the other way of conducting the research is wrong, this may be what we're left with. Martin, I don't know, does that answer your question? Looks like we got the thumbs up from Martin.
Okay, we are still waiting for questions. I think I actually would like to ask another one because you talk mostly about readability and authorships. I think there are a lot of things to discuss about authorships, of course, but about usability, I think that is also a big part of human factors that have not actually been covered, like how the patch should be presented to user in what situations is helpful. Could you comment on that?
I agree with your claim at two levels. There are a lot of ilities in software engineering or programming languages for non-functional properties. And one of the issues with automated program repair evaluations is that many different papers go after slightly different approaches. Like the PAR paper, which I love a lot, asked humans, is this acceptable? Human acceptability isn't necessarily the same thing as, say, the work of Zach Fry asking, is this patch maintainable? Probably they correlate, but it may be that like a change to a repair algorithm that improves one might or might not improve another. So one of the things I encourage us as a community to do is to either sort of standardize or be a bit more precise. Sometimes we'll just say patch quality, but think we're talking about maintainability or usability. Now for usability itself, you asked both how do we present these patches to humans, but also, are we measuring things like usability? And my apologies, I don't have an encyclopedic recall of the literature, but I'm not aware of any or that many papers that look at the effects of different types of presentation. Like, is this centered in the screen? Do we do syntax highlighting on whether or not patches are accepted? Some of the psychology work I cited earlier did try some versions of like removing all the spacing in the indenting in order to make that part look worse. But that's not the same sort of thing you're talking about. I actually think it would be nice to look at the sort of UI, UX aspects of automated program repair, like what's the best interface for presenting those to people? Because some of the interfaces we use in, for example, GitHub to do pull requests assume that there's some sort of like chatting aspect or that you can communicate with the other dev that might not be possible here. I regret that my answer is a kind of an I don't know, but I agree with you. Usability is understudied. I think we should do it more. Maybe we can work with our collaborators in HCI.
Mm-hmm. Thank you for the answers. I think we still have actually just a few, less than a minute for one more questions. I think like if the questions is not because after this end, okay, we get one more questions. But I like 8 seconds. How do the practitioners